Have you ever wished you could pause time, rewind the past, or glimpse the future? While these ideas are common in science fiction, there's a growing area of speculative science called chronotechnology, the theoretical study and future possibility of controlling, manipulating, or engineering time. While we currently have no working technology to move through time like we move through space, modern physics does suggest that time is not as rigid or untouchable as we once thought. Let us start with a question. Is time really a constant flow, or can it be bent? According to Einstein's theory of relativity, time is flexible. It stretches and compresses depending on how fast you move or how close you are to massive objects. Astronauts on the International Space Station, for instance, age slightly slower than people on Earth because they move at high speeds. This effect is tiny but measurable, and it proves that time is not absolute. This is the first clue that time can be manipulated, at least in extreme conditions. Now imagine taking that further. What if we could use technology to slow down or speed up time locally, or even create loops in time? These ideas form the basis of chronotechnology. Scientists have theorized concepts like closed time-like curves, paths through space-time that loop back on themselves. Some models, like the Gödel metric or Tipler cylinders, allow such loops in general relativity, although they require impossible conditions like infinite length or Still, the math suggests that time manipulation is not forbidden by physics, it's just extremely difficult. Could we build a time machine? So far, no, but some real-world experiments hint at early steps toward time technologies. For example, quantum entanglement allows particles to affect each other instantly across distance. And some interpretations, like the transactional interpretation, suggest influences may go backward in time. Also, in quantum mechanics, time doesn't behave the same as in classical physics. In some labs, scientists have even simulated time reversal in small quantum systems using advanced algorithms and error-correcting codes. Another area of interest is chronobiology, not time travel, but engineering biological time. Scientists are learning how to pause metabolism, extend lifespans, or even hibernate organs for future revival. Think of astronauts sleeping for centuries on long voyages, or patients frozen in time until cures are found. This is not time travel in the classical sense, but it is a form of controlling how organisms experience time. Let's consider an example. Imagine a spacecraft that travels near the speed of light for 10 years. Thanks to relativistic time dilation, the astronauts inside might experience only 2 years. When they return, Earth has aged much more than they have. This is not fiction. This is proven physics. Future chronotechnology might find ways to use this effect intentionally to send people or messages into the future. The challenge is achieving the required energy and velocity in a practical way. So could we ever go back in time? This is much harder. The laws of thermodynamics, especially entropy, suggest that time flows in one direction. Some scientists argue that time's arrow is tied to the expansion of the universe or the flow of information. To reverse time would require reversing entropy or undoing every microscopic interaction in the universe, which seems impossible. However, speculative models like the many worlds interpretation or causal set theory hint that retrocausality, effects before causes, might be possible at the quantum level. Looking further ahead, chronotechnology might one day include chronoscicillation, devices that slow down or pause time locally, useful for surgery, escape, or precision measurements. Chrono-recorders, tools that trace all changes in a region, essentially creating a black box of time for forensic science. Time-beamed communication, quantum-based systems that send information into the past under strict conditions. Chronoresonance, devices that interact with past or future quantum states using field manipulations. Purely theoretical so far. What are the dangers? Time manipulation, if possible, would come with huge risks. Causal paradoxes, like changing the past to prevent your own birth, could create logical inconsistencies. Even in controlled settings, temporal instability could affect biological systems, information flow, or energy conservation. This is why most scientists treat chronotechnology with extreme caution, even in theory. In conclusion, chronotechnology explores the outer edges of physics, time, and what it means to exist. While it remains speculative, it is rooted in real science, from relativity to quantum theory, and may one day lead to profound breakthroughs in aging, communication, and perhaps even our understanding of free will. Whether or not we ever build time machines, chronotechnology is teaching us that time is not just a background, it may be a tool we can learn to shape. Chronotechnology refers to the hypothetical manipulation, measurement, and engineering of time, including its flow, structure, directionality, and synchronization. Unlike conventional technologies that operate within time, chronotechnology aims to treat time as an active, controllable dimension, much like space, mass, or charge. It spans potential technologies for time dilation, time perception modulation, causality management, and even temporal navigation. Chronotechnology requires advanced understanding of relativity, quantum mechanics, and thermodynamics, where time is not absolute but dynamic. At its core, it explores whether time itself can be shaped, paused, accelerated, reversed, or segmented for functional use. Atomic clocks that exploit relativistic effects aboard satellites are primitive forms of chronotechnology used in GPS, like learning not just how to ride a river's current, but how to change its speed, flow direction, or split it into branches. Einstein's theories of special and general relativity show that time is not fixed. It dilates based on relative velocity and gravitational field strength. In special relativity, time passes slower for objects moving near light speed. In general relativity, it slows near massive bodies. Chronotechnology could one day use these effects deliberately, engineering environments where time flows at customized rates. Such environments may be useful for computational acceleration, longevity zones, or asynchronous processing systems. Mastering time dilation engineering requires precise control of mass energy distribution or sustained high-velocity systems. Time on the International Space Station passes slightly slower than on Earth due to both velocity and gravitational differences, like walking slower or faster depending on whether you're going uphill or downhill. Except the terrain is gravity and the pace is time itself. Chronotechnology includes the development of ultra-precise timekeeping and synchronization systems, which are critical for navigation, communication, encryption, and quantum coherence. The evolution from mechanical clocks to atomic and now optical lattice clocks has pushed precision into the attosecond, 1018s regime. Future systems may achieve synchronization at the zeptosecond or yoctosecond scale, enabling distributed quantum networks and relativistically stable communications. Chronotechnical advances in synchronization are also vital for interplanetary or interstellar navigation, where relativistic time drift becomes significant. It may also allow for predictive modeling in complex systems, where microscopic time shifts reveal macroscopic trends. GPS satellites are corrected daily for time dilation errors to maintain global positioning accuracy, like tuning a symphony where each instrument plays in sync even when they're in different cities. Chronotechnology also applies to biological and neurological time, influencing how humans perceive, process, and act in time. Our brains run on temporal integration windows, which define attention span, reaction time, and motion prediction. By modulating brainwave states or neurochemical timekeepers, e.g., dopamine or circadian hormones, one could alter subjective time flow. Applications may include enhanced learning, slowed perception during critical tasks, or treatment of neurological time disorders like Parkinson's or ADHD. This domain bridges neuroscience, chronobiology, and extended cognition. Athletes and soldiers often report slowed time during high-stress moments, suggesting neurochemical modulation of time perception, like adjusting a camera's shutter speed to capture more or fewer moments in the same second. Time-based storage systems could encode data not in space, bits, atoms, but in temporal patterns, such as delays, sequences, or time-dependent quantum states. This is essential in quantum memory systems, where entanglement and decoherence depend on ultra-precise timing. Temporal encoding may also apply to non-volatile computing, where information persists by oscillating in closed-loop temporal sequences. Biological systems already exhibit time-cast-in learning through synaptic plasticity and spike timing-dependent plasticity, STDP. Chronotechnology could develop hardware inspired by biological time-based learning and memory consolidations. Quantum dot systems have demonstrated memory behavior based on oscillatory timing sequences rather than spatial storage, like storing a melody not in written notes, but in how and when you hum each tone. Chronotechnology may enable systems that modify or shield cause-effect chains, especially in quantum systems where retrocausality or indeterminate histories are mathematically permitted. Temporal logic gates, devices that operate not just on states but on sequences of events, could be developed to filter causal relationships akin to logic and time. Such systems could be used in quantum cryptography, dynamic decision-making AI, or time-based event filtering. Causal manipulation might also be useful for defensive technologies, interrupting signals before they cause harmful actions. The logical structure of time becomes a domain of computation, not just physics. Delayed choice quantum eraser experiments suggest that choices made in the present can influence the history of a quantum event, like reading a detective novel where your guess about the culprit changes what happened in chapter 1. Thermodynamic time, driven by entropy, informs why time appears to move forward and why perpetual motion is impossible. Chronotechnology might allow local reversals of entropy, enabling temporary time reversal phenomena or synthetic conditions where the arrow of time is modulated. This would require open systems, exchanging entropy or computational control of microstates, possibly using feedback-informed energy shaping. Such processes might be useful in error correction, biological repair, or information resurrection. Reversible computing and thermodynamic erasure are early theoretical steps in this direction. Some optical systems have demonstrated time reversal of wave propagation using engineered materials and adaptive mirrors, like unbreaking a glass not by rewinding video, but by engineering every molecule to jump back in place. At cosmological and quantum gravity scales, time may be nonlinear, looped, emergent, or multidimensional. Some theories predict closed time-like curves, wormholes, or quantum superpositions of histories. Chronotechnology might one day exploit space-time topologies to build devices that link distant times, create chronal isolation zones, or stabilize causality in complex quantum networks. It may also involve creating temporal shields, slowing time around critical systems, e.g., for archival preservation or long-direction experiments. Such speculative applications require integration of general relativity, topology, and information theory. Solutions to Einstein's field equations allow theoretical wormholes that connect different regions of space-time, including different times, like a bridge not across a river but across two moments in history. Chronotechnology challenges the nature of memory, identity, free will, and causality, as it implies time is editable and constructible, not immutable. If time becomes programmable, then history, prediction, and presence may blur, forcing reconsideration of ontology and ethics. Are we responsible for potential futures? Can we revise pasts without collapse? Chronotechnology thus extends beyond physics into epistemology and metaphysics, requiring careful governance of both what we can do and what we should do with time. A chronotechnical interface that lets a user undo reality events may challenge legal and moral structures based on irreversibility, like handing someone an edit button for time with no save or backup file.